Hi, I'm Rob Fields, leader of the Bearcat Hybrid Rocket Team. This is an overview of the hybrid rocket research we conducted between fall of 2015 and spring of 2016 for our senior design project. This is the third year of this project, and we have built off of the experiences of the first 2 years. The team members are myself, Brandon Mullen, the assistant team lead overseeing the propulsion group, Harrison Slater, assistant team lead overseeing the controls group, Dan Weiss, assistant team leader overseeing the structures group, David Harris, the safety and systems lead and also a member of the propulsion group, Andrew Blosser, who is in the structures group, Stephanie Matana, who's in the propulsions group, and Isaac Quay and Guy Tadaro, who are both in the controls group. The advisors over the course of this project were Professor Schaffner, Professor Orquist, Professor Walker, Professor Cohen, and Professor Tommy. The objectives for this research were laid out under Dr. Schaffner at the beginning of the project. Those objectives were to learn how to control a hybrid rocket engine, to gain experience in safe testing of rocket systems, to improve technical decision-making skills, to develop project management and teamwork abilities, to acquire expertise in fabrication and assembly of hybrid propulsion systems. And above all, the key objective was to conduct this research safely and responsibly, as operation of rocket systems inherently poses major risks. Our initial budget for the project was $6,500. Our actual spending came in well below that at $1,826.72. These cost savings were due to using the UC machine shop and fabrication and cleaning skills that were present on our team. We did seek sponsorships and discounts from outside organizations, notable among them being getting the oxygen regulator cleaned for free. Unfortunately, none of those came through, and so we were still able to save quite a bit of money, but our budget, or our spending, was still $1,800. In October of 2015, we started with our system requirements. We had our PDR and CDR, and then conducted our first static test before the spring or fall semester was over. During spring semester, we did range calibration testing, control system functionality tests. We did a fuel fabrication study. We did more sensor calibrating, and then we conducted our second and third static tests. Immediately after the third static test, it became apparent that we needed to conduct a failure investigation and revisit our risk analysis. Those were complete by April 21st. Our final presentation was the next day, April 22nd. The basics of a hybrid rocket system are that a liquid or gaseous oxidizer is blown into a rocket body containing solid fuel. The combustion of the oxygen and fuel mixture is then blown out the nozzle, producing thrust.
Hi, I'm Harrison Slater. I'll discuss some of the main points of operation for the hybrid rocket. The static stand should hold the rocket body and will measure thrust. The steel rocket body contain the solid fuel and the nozzle. Gaseous oxygen will be supplied through the control system. Ignition will be done by a remote igniter. There will be a burn time of approximately 13 seconds. And combustion should cease when oxygen is cut from the rocket.
Here to discuss the new additions to the hybrid rocket design. First on the list is the data acquisition system. The purpose of this is to relay testing data to a ground control station during test firing of the rocket. The test of this was successful. The data related to the ground control station was thrust data, load cell data. The pressure chamber data is currently being evaluated, and the thermocouple data can also be relayed. The next item is the reusable ignition system. After some initial testing and research, this design was found to be unusable.
I'm about to describe the static test stand, or static test environment. Here, we see our oxygen supply. The hose leads back behind the shipping container where oxygen shutoff is located. Follow the hose down here is our orifice plate and flow measurement system. Continue to follow the oxygen line into the rocket stand. Here's where our data acquisition system will be mounted. Here's the rocket body and our containment for the exhaust. I'll show an up-close view of the rocket stand. Again, following the oxygen line into the body, ahead of this plate is a blow-off valve. Just here on the other side of the plate is the transducer to measure chamber pressure. Here, currently being prepared to be mounted is the data acquisition system, the top of the flange. Here's the rocket body again. Here can be seen the nozzle. Again, the containment unit for the exhaust. Here's our igniter wire being prepared for connection for fire.
Hello, my name is Brandon Mullen. As the assistant team leader of the propulsion system group, I'm presenting to you the safety and systems aspects of the hybrid rocket project. During the planning and design phases of the project, we drafted, revised, and submitted a safety procedure checklist to the spacecraft design faculty advisors. After their approval, this document served to mitigate the risks that we may encounter during the assembly and pre-launch phases of static testing. We would like to acknowledge the assistance of Dr. Samir Tambi in providing on-site faculty oversight of all static testing that occurred at the university's Center Hill Research Facility. Also, during the month of February, in preparation of a rapid testing schedule, a safety and systems integration officer was appointed. This officer was charged with the twofold mission. First, to oversee the documentation and execution of the safety standards and procedures put in place to ensure that all aspects of the hybrid rocket project were done in a safe manner. And second, communicate with the group leads and assist in the integration of the controls, structure, and propulsion subsystems.
Hello, my name is Daniel Weiss, and I am the assistant team lead of the structures subgroup. We conducted a total of 3 static tests to serve as a baseline for testing and data recording procedures. The first was a legacy test to confirm that we were able to successfully conduct a static testing. The following 2 were used to confirm that our modifications to last year's static stand allowed us to successfully gather the data required to further our control design. The first 2 tests of these 3 occurred with no major incidents. However, during the 3rd test, a snap ring responsible for holding the nozzle in place failed and resulted in the nozzle being dislodged. While we were unable to acquire meaningful data from the 3rd test as a result of this, there were no injuries or damage occurred. It was a substantial enough event, though, that the team decided to halt testing and conduct a full failure investigation. The results of this investigation are detailed in our final report. As a result of the investigation, however, we were able to get back on track and are now ready to continue testing and future progress of the project. The next step that should be taken for this project is to implement the findings of our failure investigation. The most important of these is that the possibility of replacing the snap rings in the rocket body with a fastener that is less sensitive to heat transfer. Also worth noting is the future use of non-concussive igniters, as our igniter was thought to be one of the causes of the failure during the 3rd test. Also important is there is a potential of repeated use increasing the failure chance of the rocket body. This is something that should be inspected after every test. Following these steps, the project is ready to be continued by future classes. Though we recommend that in the future, smaller milestones be used in order to meter the pace of progress and ensure that realistic goals are set and can be achieved. This project also needs more faculty and expert oversight, as this will help future participants be successful and also be safe.